Good morning to everyone. We are from Group 1, Section 3, BEV40702 Power Engineering Laboratory. So the title for this subject is Simulating Power System Response for Power System Stability of Electrical System Simulation Laboratory. So here's our team members. First of all, Adi, Aina, Arif, and me, myself, Charan Khan, with metric number AE2045. So our content consists of 4 parts. First of all, introduction. Secondly, methodology. Third, result and discussion. And last but not least, conclusion. So let's move to the introduction part. An electrical power system consists of a complex component that generate, transmit, and deliver electricity to various customers, ensuring its safety, reliability, and efficacy. So it also is a evaluation of power systems and have a great impact of digital computing. For the background, power system stability simulations ensure grid safety and reliability. Engineers also use simulation to find flaws and test mitigations. Dynamic behavior modeling capture system fluctuations and also improve system efficiency and reliability. There are two objectives in this project. First of all is to model a test system model of power system using MATLAB and also to analyze the dynamic response of the system. There are 4 scopes. First of all is to create a comprehensive power system test model using MATLAB, recreate various power system, component and dynamic, and also investigate system behavior under different operating settings and also simulated some disturbance. That's all from me. Thank you.
Hi, my name is Adi Iskandar Bisavia. My metric number is DE210092. So for today, I will be continuing to explain to you about the methodology. So the chapter details methodologies uses for this project study. So focusing on reviewing the project's components and operational flow. So for this lab session, we are going to discuss about power system stability. So what is power system stability? Power system stability is the ability to resume stable operation after disruptions involving dynamic, transient, and steady state stability. Instability occurs when the system loses synchronism and when synchronous machines go out of phase. So for this lab session, we are going to use MATLAB Simulink. So we utilize this model to simulate dynamic behaviors, which is voltage stability, transient responses, and small signal stability. So and the power system components are generators, transformers, transmission lines for stability analysis and control system design. The clearing critical time, which is protective devices response to clear a fault, and critical angle, maximum rotor angle deviation before losing stability, are determined through simulation, monitoring the system's transient response to disturbance. So engineers iteratively adjust parameters or control techniques based on simulation results to meet stability criteria, ensuring the reliable and stable operation of power system. So I will be continuing to explain to you about the second disturbance, which is sudden large decrement at bus 7. So as you can see from the graph, the circuit breaker in area 1 is set with a switching time of 7 seconds and an initial status of close. So the disturbance involves a load decrement of 50% more than the original load. So as you can see, the graph shows the rotor angle, theta, and the rotor speed of the motor versus time, indicating system instability at 2 seconds, where the switching at 2 seconds leads to system stability. It happens with a voltage spike caused by the abrupt drop in load, resulting in a power surge before system failure. So the procedure disconnects the load from the power supply rather than lowering it gradually, leading to the load being effectively shut off from the circuit when it loses electricity.
Assalamualaikum. My name is Arif Nakiuddin Suzukaman. My matrix number is DE210113. Okay, now I will continue with disturbance number 5, which is temporary voltage 3 phase fault at bus 8. So at first, all 3 phases of bus 8 experience a short circuit, causing a surge in current and a significant voltage dip, which means there is a sudden spike in the current graph or current value and voltage drop. So, the switching time will happen at uh, 1 second to 6 seconds, and that is the faster clearing time. So during the clearing time, PSS is stabilizing the system from the faulty condition to steady state condition or stable condition. So how how the PSS responds? So basically, PSS might send a small corrective signal to the generator control system to help it return to nominal speeds, and relatively smaller voltage dip due to faster fault isolation, and then generators experience a slight decrease in speed but are more likely to recover quickly and maintain synchronism. Okay, here I will continue with the results from the simulation. So these four um, are the result that have been categorized into two condition, which is stable and unstable conditions. On the left side, we have 1.1 second and 1.3 second, which is the stable condition. So um, in the graph, we can see initially the system have fault or short circuit happens in the system, and then after 1 second to 6 seconds, the PSS is stabilizing the system from the faulty condition to steady state conditions. Same goes to the 1.3 seconds, because it also a stable condition, because the switching time is 1 to 6 seconds, and those range and those duration is still in the range of the switching time. And on the right side, are the unstable conditions. We can see here, obviously the switching time is below 1 second, uh, which is 0.5 second and 0.5 seconds. So the circuit breaker or protective relay cannot be operate at at the periods. So the surge current and voltage drop continuously happen in the system.
So this is the permanent board three-phase fault at bus 8. So permanent three-phase fault at bus 8 use a fault generator block. Fault generator connected between transformer T1 and 25 km nominal P1 transmission line in area 1. Observation focus on behavior of the generator's machine in area 1. Recorded data include rotor angle speeds and electrical power. Generator 1 and 2 exhibit increasing rotor angles, and generator 3 4 remain stable. Critical curling time identified 0.5 seconds and critical curling angles as 40 degrees.